Hi folks, welcome back to Physics with Captain Rod. Purpose of this video is to give another example of how to use Gauss's law. This example is going to have what's referred to as planar symmetry. So imagine, if you will, a total charge Q spread out over a flat surface of area A. Imagine this is a very large sheet of charge. So imagine kind of a rectangle or a square with a charge distribution spread out over the surface. Right now, this is supposed to be like a little eyeball. So if we were looking at like this from a side view, basically this is what we would see. It would look like a line of charge from looking from this way or maybe from this viewpoint. Right? And what we're going to do is we're going to try to find the electric field at a point, at some place above this, some height, let's just say h, up above this sheet of charge. So maybe in this picture over here, we're talking about maybe right here, a distance h for height away. So, yeah, again, the idea, how can we find the electric field? Now, finding electric fields, there's three different ways. The two most common ways are this. One, we know that the electric field due to a point charge is equal to kq over r squared. I've made other video examples where we took this, and what we do is we break the charge distribution up into a bunch of chunks that are point charges, and it becomes an addition or an integral type of process to find the net electric field. And, we could do that here, but it's a lot more challenging a math problem than it looks like. This picture makes it seem like it's kind of a one-dimensional charge distribution, but it's not. The charge dimension's in two dimensions here, really. And if I pick like an element of charge here, this is going to give me an electric field in one direction. But if I move over to here, the electric field at this point in space, it's changing in magnitude and direction, and it's a three-dimensional problem. So long story short, it's a lot of math. It's a very, very difficult problem to try to find the electric field by direct integration. So what we're going to do instead is we're going to try to employ another method here. We're going to try to use Gauss's law to find the electric field. Now, Gauss's law, very handy law for areas of high symmetry. And this is a very symmetric problem as long as we make a certain set of assumptions and we stay within certain boundaries. If you look at this point right here, or right here up above the center of this is a pretty symmetrical problem. The electric field right at this x here, which is at a point just above this surface, is due mainly to the charge in this region. As long as this point here isn't out here towards the end, this is a very symmetrical problem. So what we're going to do is we're going to apply results only kind of in the center, and we're going to use Gauss's law and a Gaussian surface. So the first thing we have to decide on is what type of Gaussian surface to draw. So what I'm going to do here is I'm going to draw a surface. It's going to look kind of like a cylinder here. And you got to imagine this kind of extends down below as well. It's important that the surface be a closed surface. So there is my Gaussian surface. I'm even going to label it here, GS here. Right? In the picture on the right, if I was doing kind of a side view, this is kind of what we would see. Boom. Now, this thing looks like kind of a beer can or a pop can or something like that. Now, I'm going to use mainly this picture on the right here to do my math. So I'm going to write out Gauss's law, which says this: the total electric flux, which is the, and again, I'm going to work this once kind of in an algebraic method and once using an integral method so that I can get away with one video here for two classes. I'm going to give myself a little room here. Start over here. The total electric flux, which is the sum of all the EA cosine thetas. Oops. The sum over the body, or surface, is equal to 4 pi k times the charge inside the surface. And again, I can write the same equation basically in integral format. It would look like this. The total flux, which is the integral, E dot dA over the entire surface, is equal to 4 pi k times the charge inside the surface. So again, these equations are basically saying the same thing. One is just a little stronger mathematical way to say it. All right, so as I consider my Gaussian surface here, we got some dimensions. This has a certain radius, r. Now, by the way, I chose a cylindrical type surface. You don't have to choose a cylindrical type surface. I could have just as easily made maybe a little rectangular deal or a cube. In fact, I can use any surface area, any type of geometry I want for that top surface area. And what we'll find is that it divides out later here in the end. I like to use little cylinders when I'm drawing my Gaussian surfaces. So my Gaussian surface here has a radius r. This dimension is h. I drew it symmetrically, so it's h on this side as well. And now I'm going to start kind of evaluating the left-hand side. I'm just going to kind of do both equations at the same time. All right. EA cosine theta, where the angle theta is between the electric field and the normal. If I were to draw the normal on this top surface, the normal points maybe something like that. The normal on the bottom surface points down. Normal on this side surface, now it depends on where I draw it on the can. I'll just kind of draw it like this way. It's important to note that the normal points at a right angle to the surface of the can. Right? So when we do the calculation over all three surfaces, we have to consider the electric field vector at each surface. Here, the side can, and the bottom surface. I'm going to draw the electric field vectors in red. So looking at this problem, and taking note that this problem is symmetrical, there's basically as much charge on the left as there is on the right. The electric field at this point is due mainly to the charge in this region. As far as that region is concerned, it's a symmetrical problem, so the electric field points up. Whoops. Getting a little close to the top of my computer thingy. It does not like it when I do that. All right, so there's my electric field vector here. The electric field vector, same argument on the bottom surface, points maybe down. The electric field anywhere on this vertical surface is going to be up if I'm up in this region, down if I'm down in this region. So now, when we do EA cosine theta on the top surface, that's going to be the electric field times pi r squared. Notice that the angle between the electric field and the normal is 0. Cosine of 0 is 1. That's why we just end up with E times the area. It's important to note what area I'm talking about. That area right there. So that's, and since that's a circle, it's area pi r squared. That flux term would be positive because the electric field and the normal are in the same direction. Or you could think of it like this. The electric field is pointing out of the surface, and generally speaking, outward is positive. Okay, plus. Now I'm going to consider the side can surface. So the can surface here, again, if you picture an electric field vector anywhere on that outer surface, the electric field vector is either up or down depending on, am I up in this top region or in this bottom region. No matter where I'm at, the angle between the electric field and the normal is 90. Cosine of 90 is 0. So there is no flux through the side can surface. I'm just going to put 0 for the can. Down here, electric field down. Normal down, angle between them 0, cosine 0, 1. So the cosine theta is 1. So we're just going to have the electric field times that cross-sectional area, which is pi r squared. And all three surfaces have been considered. So I have summed up all the EA cosine thetas on that can. Right, equals 4 pi k charge inside the surface. Right. We talk about what would this look like here if we're working this, the integral form of this equation. It looks basically the same. I might go back and just add, all right, to this normal vector, if I just put dA in front of it, it's now what I would call the dA vector for the E dot dA. Same thing here. I'll just put a dA right here, same thing here. So these are now in green. I've basically just kind of converted those to what I call the dA vectors. Remember that the dA vector is a vector we make up. Magnitude is area. It's in the normal direction. So the E dot dA on the top surface is magnitude of E, magnitude of dA, cosine of the angle between them. I guess I would take note here that there's no reason for the field to vary along this surface, so basically the electric field is constant on the integral. It can come out in front. So long story short, we just end up with E times the integral of dA, which is pi r squared. on the top surface. On the side surface, the E dot dA is 0 because anywhere on this side surface, the angle between the electric field and the normal is 90, cosine 90 is 0. The E dot dA on the bottom surface, also for all the same reasons, is equal to the electric field times pi r squared. And again, I'm using the assumption that the electric field is constant anywhere on the surface. It's not varying, therefore it can come out in front of the integral. And then you just have the integral of dA, which gives just A, basically. So right-hand side, 4 pi k q, charge inside the surface. So whether we're working this out in an algebraic sense like I did on the left or using integrals doesn't really matter in this problem. All right. So next, on both sides here, we can write this: 2e pi r squared equals 4 pi k. Now we start working on the charge inside the surface. So the charge inside the surface is this stuff. In this picture, we're talking about just that region, and over here, we're talking about just this stuff. We can find that in similar to how we take a charge distribution and break it into little point charges, and then find the charge of the point charge on the point charge. Because this is a surface area problem, if I take the total charge, divide by the total area, right, I have what's called the surface charge density, and then all I have to do is multiply that by the area of my Gaussian surface. And the area you need to multiply by is the circular area. Like if I'm looking down, you would see that circle. That's the area that's enclosing that charge. So if I take Q over A times pi r squared, I now have the charge inside the surface. This is true regardless of which equation I'm using or which type of math I'm trying to apply to this. So 4 pi k times Q over A pi r squared. And now what we have is we have an expression here that we can just algebraically solve for the electric field. I'm going to go ahead and just keep solving this one, taking note. This is the same equation here. So from here on out, the problem's identical on both sides. So let's see. A pi will go away. R squared also gone. So the electric field strength is going to equal, in this example, let's see, 4 over 2 is 2. We still have that pi. The Coulomb constant stays, times Q over A. So there's our result here. And there's some things to take note of. You'll notice that the height right here doesn't matter. That geometry never comes into play in this problem. And what that tells us here is that this is some number, it's some constant as far as this particular problem is concerned. It says that the electric field now is uniform, it's not varying height, and it's proportional to a Q, falls off with area. So this is called the charge density, the area charge density. If you look this up in the book, it might say something like 2 pi k times sigma. Sigma is what's called the area charge density, right? So this would just equal total charge per unit area. Important parts about this problem are this. It's not important that you memorize this. It's probably reasonably important to recognize that when you have large sheets of charge, you have a constant electric field close to the sheet. We're not talking about towards the ends, because that's not true in the end regions, but as long as we're talking about in this region here, right above or right below the charge, we have a nice uniform electric field. Other important things are how to apply Gauss's law. So you'll notice that I drew a Gaussian surface. That's the first thing you always are doing here. It's right there in this picture. Multiple pictures of different viewpoints also helps. There's my Gaussian surface here in this picture. Your Gaussian surface needs to be a closed surface. It needs to be able to hold water in any orientation, basically, because Gauss's law only applies to closed surfaces. That's what this symbol is about here in this integral. Then you draw electric field vectors at every relevant point on that surface, right? And you draw normals or dA vectors. It's kind of your choice. You draw them so that you can evaluate this, the cosine theta, because that cosine theta is the angle between the electric field and the normal. Or in this example, so that you can evaluate the E dot dA. Keeping in mind the dA vector is in the direction of the normal. Okay. Then you hope for symmetry. In these examples, in most Gauss's law problems, you hope that the electric field's constant and can come out in front of the integral. And then you typically have to figure out how to write the charge. That's where you get this is going to depend on the problem. Sometimes it's just a bunch of charges sitting there, you just add them up. Sometimes it's a charge distribution, and you have to use either a linear charge density or an area charge density or a volume charge density. That'll vary case by case. Write out Gauss's law. Usually it results in something that you can just solve for the electric field. So hope that this example helps demonstrate that, and have a great day.